Ladies and gentlemen, I'll wait for the last few people to take their seats. Thanks. Ladies and gentlemen, members of the Faculty of Science and Engineering, members of the board of the Studium Generale, my name is Scott Traeger. I'm the director of the Kaptein Astronomical Institute here at the University of Groningen, and I would like to extend my welcome and that of the Kaptein Institute to all of you on the occasion of the 2019 and 21st edition of the Blaauw Professor Lecture. This year, we are very pleased that the Blaauw Professor Lecture will be given by Professor Marta Volonteri of the Institut d'Astrophysique de Paris and the University of Amsterdam. We are especially pleased to welcome tonight members of Professor Blaauw's family, including his daughter, Bina. Welcome, Bina. I will now give the word to Professor Bartel, also of the Kaptein Institute and host of this year's Blaauw Lecture.
Pleasure to see so many people. I'm Peter Bartel, professor in the astrophysics of active galaxies that will be dealt with to some extent tonight. Please put your phones in silent mode. During the past 2 or 3 decades, astronomers have discovered many cases of an ultramassive black hole in the center of a galaxy. Ultramassive means millions to billions times the mass of a sun. And that includes our own Milky Way galaxy. And it is now believed that these central black holes are an integral part of galaxies and that they grow while the galaxies grow throughout the history of the universe. The 2019 honorary Blaauw professor, Dr. Marta Volonteri, is an acknowledged expert in this field. And we should be extremely pleased that she wants to share her knowledge and her excitement with us tonight. She obtained her doctorate in Milan, then took up positions in Santa Cruz in the United States and Cambridge, England. Subsequently, she became assistant and later associate professor in Ann Arbor, Michigan in the United States. And from 2012 onwards, she has been directeur de recherche at the Institut d'Astrophysique de Paris. She was recently appointed as a part-time professor by special appointment, bijzonder hoogleraar, at the University of Amsterdam. I vividly remember that I was fascinated in 2012 when I read her review in a special black hole issue of the famous Science magazine. And I have no doubt that we all will be fascinated tonight. The floor is yours.
Thank you very much, everyone. It's really an honor to be here. And I want to thank the Kaptein Institute, the Faculty of Science, Studium Generale, sorry for my accent, and the family of Professor Blaauw for giving me this option. And I really treasure this option because I hope I can share with all of you my passion and my enthusiasm for this research that I've been conducting at this point for many, many years, trying to understand the formation, the growth of evolution of black holes in galaxies. So today we will talk about black holes as astrophysical objects. We're not going to talk about wormholes, white holes, firewalls. We're going to be really in our universe, in our galaxy. We will look at the center of the Milky Way. We will look at nearby galaxies and try to understand what is the role of massive black holes in all this. They're actors in the cosmic evolution of galaxies. We see them, and what I've been curious about for the past, 20 years now is how did they get there? And so today I will share with you what I've learned and the questions that are remaining and we're still working to solve. So let me start with black holes. Why black holes? This is something that I'm sure all of you have heard before, but it's worth repeating. We call these black holes because they're black and they're holes. They are objects that are so dense that the speed, escape speed from these objects is larger than the speed of light. So photons, light, cannot leave the black holes once they fall in. So nothing from inside can come outside and tell us what's there. We will see later that although this makes the interior of black holes invisible, in reality, they produce a lot of energy. So this is not a contradiction, and we will go through this. But the other things that I think are curious about black holes is that the astrophysical black holes are the simplest objects in the universe. Two black holes that have the same mass, so the same amount of weight, and rotate at the same speed are indistinguishable. Now, this is not true for everything else. Two people like us, if we say that we have the same height and the same weight, and we pace this room at the same speed, well, there are still many, many other parameters that make us different. For black holes, this is not the case. Just these two numbers define two black holes, that they will be absolutely identical. The reason is that information on what made these black holes is erased when it goes inside. In our case, everything that we went through in our life is still with us. That's what makes us different. So, although black holes technically are very, very simple, in practice, they're complex. They're complex not in their inner workings, although if you were a theoretical physicist, you would say, yes, they're complex also in that sense. But if you're an astrophysicist, they're very complex in the way they interact with their surroundings, with the rest of the galaxies, with the rest of the universe. And this is, to me, the most exciting part about their evolution. So as Peter was saying at the beginning, we have two types of black holes that we study. One are stellar black holes, what I will call stellar mass black holes throughout this lecture. These are black holes that we know very well. We have known since 1970 or so, the early 1970s. These are black holes that were created by the end of the life of a massive star. If you have a star that is about 10 times the mass of the sun, it will end its life creating a black hole with a mass of about a few times the mass of the sun. We have known this for a very long time. In 2015, we had a breakthrough in understanding them because we detect the gravitational waves from merging black holes, from merging stellar mass black holes. These black holes were much more massive than any black hole we have seen before in this stellar mass category. So we're learning more about them. So we know that how they form as the endpoint of the lives of massive stars. We know that their masses are up to 10 times, 50 times the mass of the sun. Then we go to the other group, my black holes, massive black holes. In this case, the lowest mass black hole that we know of this group is 20,000 times the mass of the sun. The most massive that we know is more than 10 billion times the mass of the sun. So we're really talking about something that is very different from the stellar mass black holes that we know. These are objects that weigh as much as an entire galaxy. In the Milky Way, the total mass in stars is about 10 billion times the mass of the sun. There are about 10 billion stars in the sun. There are black holes that weigh as much as this. How did they get there? How can we form a black hole that is as massive, that weighs as much as an entire galaxy? I mean, this has been what I've been asking myself for many years. So here I put some pictures of one of my favorite black holes. I have 2.5 favorite black holes. I will show you the half in a minute. And the second is coming after this. So this is a black hole. This is the galaxy. So you see here on the bottom panel. On the left, you see an image of a galaxy called M87. I mean, galaxies don't have always pretty names, but this is a galaxy. It is it's a giant galaxy. It looks like a big sphere made of stars. You see here a quarter of the galaxy with the center, and you see a jet coming from the center. This is a jet. Let's see if this works. No. So this jet is a signature that there is a black hole in the center. Now, last year, in April 15, April 10th last year, the Event Horizon Telescope collaboration actually took a picture of that same black hole. Now, the picture on the left is on scales larger than this galaxy. The picture on the right is a few Schwarzschild radii from the center of that black hole. So we have a picture of an enormous black hole. This black hole has a mass of 2 billion times the mass of the sun. And it's one of the most massive that we know. So we have a picture of its interaction with the galaxy through this jet, through this ray of light that you see. And we have a picture of photons, of photons very, very close to the event horizon. So these are scales that are separated by many orders of magnitude. So here I put together the populations, what we know about these two types of black holes, the stellar mass black holes, the little black holes that are formed from the end of life of stars, that are shown here with the orange blob, and the blue blob are the massive black holes. You see here that that's why I said we know of two groups of black holes, because there is a hole in between. Observationally, we know about the stellar mass black holes with mass up to about 60 times the mass of the sun. We know about these massive black holes with masses from, say, 20,000. This is the record holder, to 10 billion solar masses, the other record holder. And what's in between? Is there something there? It depends to whom you ask. I'm a theorist. I make predictions. I use pencil and paper. I make up stories about what I think should be there. Well, the stories are based on physics, on equations. But still, I try to think of what theoretical physics related with astronomy would tell us is in there. And then you talk to observers, like Peter, who actually tries to see if what I say is right or wrong. And in many cases, like in this particular case, this hole in the middle, these black holes in this mass range where there is nothing, is where we have predictions, and I will go back to that. But observation, it's very, very hard to see if there are black holes in there. We have what we call candidates, meaning that they have observed some things that kind of look like a black hole with a mass in between, say 1,000 solar masses. But it's very, very hard to prove that they're actually black holes. And that's why they're candidates. And probably they will remain candidates for a bit. But then, in a few minutes, I will go back to what I think, to what theorists say should be in there, if there should be really a hole or not. So let me start by explaining the title now. Massive black holes at the heart of galaxies. What is a galaxy made of? It's mostly made of three things. We have a dark matter halo. About 30% of the energy density of the universe is in this dark matter, something that has a weight but doesn't emit any light. So we think that most of what composes a galaxy is actually of this dark matter. And we think that it's in the shape of a halo, meaning a big ball of dark matter. At the center of this distribution of dark matter is what we actually see with our telescopes, with our eyes: stars and gas. So here, if I take the Milky Way as an example, the mass of the dark matter halo of the Milky Way is about 1,000 billion times the mass of the sun. It's not a huge galaxy, by the way. It's an average galaxy. The total mass in stars and gas is a bit smaller. It's about 10 billion times the mass of the sun. What about black holes in there? Well, if we look at a black hole in there, the mass of the black hole that we expect, and I will show you its picture in a minute, is about 1 to 10 million times the mass of the sun. This is the typical case for a galaxy like the Milky Way or Andromeda, our sister. But now focus on the scales, on the physical scales. The size of the dark matter halo is about 100,000 light years. It's relatively big, even for astronomical standards. The extent of what emits light, stars and gas, is 10 times smaller. But now if we look at the black hole, it's super, super tiny. It's about 1/1,000,000th of a light year. It's a tiny object in the center of a big galaxy. So when we try to understand the evolution of black holes in galaxies and galaxies in the universe, we really have tried to connect all these scales in a coherent picture, from what happens on large scales to what happens in the very center. And speaking of very center, let me introduce you to our black hole. Its name is Sagittarius Star. Its mass is 4 million solar masses. Here we're taking a trip, a journey to the center of the Milky Way. You see here this dark stuff? It's what we call dust. It's like fog. It's very hard to see through, unless you use infrared light. Infrared light can pass through this fog. And then we can start looking at stars behind this fog that are at the very, very, very center of the Milky Way. This is the center. It's called the nucleus. You see here how many stars are there. They're really, really compact. The density in stars is about 1,000,000 times higher than in our neighborhood. If we go even deeper, we start seeing single stars. Now, using very, very advanced technology, here we follow individual stars in the center of the Milky Way. Look at that star out there. It's called SU, the one that moves very fast. And you see that now, oops, it is very close to another object that is not very luminous. Here we follow its motion. Really, this is real data taken on the telescope VLT in Chile, where we can trace that the star moves around an object that weighs 4 million times the mass of the sun. The luminosity of that object is not very large, but we know that it's sufficiently massive to determine exactly how all these stars complete their orbits. So using the same ways that we use for the solar system, we can measure the mass of the sun by just looking at the orbits of planets. Here we do the same. Just looking at the orbits of these stars, we can measure the mass of what is in the center. It's 4 million times the mass of the sun, but it's not 4 million times luminous as the sun. It's a black hole. So this is another image of this black hole. Now this is actually a simulation, but it tries to show what happens when a small lump of gas goes near the black hole. You see here that there is a swirling of photons. These are all photons. These are things that we can see with our eyes. When gets close to the black hole, it starts moving very, very fast, close to the speed of light. Gas that moves very, very fast becomes also very, very hot. And hot gas produces light. So in fact, when we say that black holes are black, the inside of black holes are black, is dark, but the outside is bright. It's bright whenever a parcel of something, a bit of a star, a bit of a cloud of gas, if you go too close, cross the event horizon. At that point, the gas or the star or whatever you have, initially it gets very, very hot. It starts producing this strong light. Eventually it crosses the event horizon, and the fraction of the mass of this object becomes really energy. Everyone knows energy is equal to mc squared. This is what we see in many cases. We see it in the sun, we see it in black holes. In fact, the amount of energy that we get out of mass through different processes depends on a given efficiency. This efficiency is usually parameterized with a Greek letter that here you can see as epsilon. Nuclear fusion in the sun. The value for this epsilon is about 0.7%. Nuclear fusion in the sun, you take 2 hydrogen atoms, you make a helium atom, you get a little bit of energy out of this. Then multiply it for all the atoms in the sun, you get a lot of energy. But it's a process that has an efficiency of 0.7%. Is it high or low? Well, it's much higher than anything we have on Earth. It's much higher than chemical processes. We would love to have nuclear fusion on Earth, because that would be something that would give us lots of energy. But compared to black holes, it's nothing. The efficiency of black holes is more than 10 times higher. 10% on average of each bit of mass that crosses and goes into the black hole becomes energy. So 90% of the mass goes inside the black hole, it grows its mass, and 10% becomes light. Light that we can see. That's how we can study black holes. They're actually energetic. They emit lots of light. They are among the most important sources that we can study with our telescopes. And so when we see our own black hole, that's kind of bizarre, because it defies what I just told you. It's not producing much energy. Now look at this picture. Here I have the same star that I had before in blue. It's called S2. It's a very famous star. And the black hole, Sagittarius Star, next to it. The black hole that has a mass of 4 million times the mass of that star is not more luminous. It's actually a little bit fainter. So this means that our black hole is not having some mass crossing its event horizon. Our black hole is not eating much. It's not growing much. It's not emitting much light. It's what we call a quiescent black hole. It's a very peaceful, relaxed black hole that stays there. Food doesn't get there, but it doesn't get upset. Most of the black holes in galaxies today are kind of like our black hole. They're just peacefully waiting for something to happen. This is not the case for everything. At the other extreme, we have objects that we call quasars. This is the first quasar ever discovered. It's called 3C273. Again, not a very pretty name, I apologize, but it was not my fault. So in 1963, Martin Schmidt looked at this object that everyone, almost, yeah, pretty much everyone, there were some controversies before, but thought it was a star, because it looks like a star. But this object is incredibly far away. It's about 2.6 billion light years from us. Now, if I look at the luminosity of this object, which is about 100 times the luminosity of the sun, this means that the luminosity I get from this object is comparable to the luminosity I get from an entire galaxy. It's a lot of light, really a lot of light. It's coming from a region that is about the size of our solar system. Now, this means that you need an extremely efficient engine to get so much light, so much energy from such a small amount of mass in such a small region. The only solution is a black hole. That's how quasars led to the prediction of the existence of black holes with masses of hundreds of millions of solar masses, like in the case of 3C273. Now, this black hole is not only a bit more massive than our black hole, it's about a factor of 50 more, but the luminosity is 100 billion times more. So it's not only mass that determines the luminosity of the black hole, the amount of energy, but it's really the amount of mass that crosses the event horizon. So this is a black hole that is eating a lot. It's feasting. Lots of mass is near the black hole, crosses the horizon, and produces this light. Now, this, as I said, this is not an isolated case. Well, in the local universe, today it's rare, but in the past, about 5 billion years ago, most black holes were in the same situation. They were growing like crazy, they were eating lots of mass, and they were shining. That's what we call the cosmic noon, because at the same time also galaxies were producing lots of stars. Most of the mass that we see in the universe today was produced in the past. And this time when everything was very active. And we will get back to why this is so. So now we have quiescent black holes, like our own black hole, that do nothing. They just stay there, wait. And then we have very active black holes like this. What can we learn about them? Now here I will compare for you two images. that really show the difference in this type of objects. So this first picture is called Hubble Deep Field. It's an image taken by the Hubble Space Telescope. It's one of the deepest images that we know. And each of these dots here is a galaxy. It's not a star, it's a full galaxy. You see here different shapes, different colors. This is our universe in its diversity. But each of these objects is a galaxy. And if there is a black hole in there, mostly it's quiescent. If we just look at this light, we cannot really tell that much. But then we can use different eyes, put our X-ray spectacles, and then the same patch of the sky will look like this. Now, each of these dots is an active black hole. Is a black hole that is eating, is a quasar, or a faint quasar. But now, so here if you compare these images, you will see that some of these galaxies host quiescent black holes, some other host active black holes. In some galaxies, the black holes can grow. In some galaxies, the black holes cannot. Why? Well, that's the rest of the story. In fact, what we try to do is this. We try to imagine how, starting from the universe as it was just after the Big Bang, let's say 100 million years after the Big Bang, which is when the first stars formed, when the first galaxies formed, probably the first black holes, we change, we evolve all the way to today. So both galaxies grow, they become bigger and bigger as they form more and more stars, and black holes grow as well, as they become bigger and bigger by swallowing more stuff. More black holes, some gas, some stars. But what is the pace of this evolution? And how do they influence each other? Well, here I will just show you one of my favorite ways of studying this, which is using cosmological simulations. Here you see the formation of a galaxy, a little bit like the Milky Way. Here, everything that you see in blue is dark matter. We will see some green now, in the center. This green is gas, is interstellar gas that really permeates the whole universe, but tends to condense in the densest regions. And then, in the center of these gaseous concentrations, at some point you will see forming stars. You see here the red in the very center? These are stars that are forming in the center of galaxies. And now if you pay attention, there are also some white dots. Do you see the white dots? These are black holes. In fact, some black holes form in galaxies at the same time as stars and gas evolve. So here you see that galaxy, you have seen the black holes popping up. And now what we want to do is to follow the evolution of all this, dark matter, stars, gas, black holes, for the whole 14 billion years of the evolution of the universe and understand how they evolved together. Now you see here the galaxy, these are proto-galaxies. They kind of look like galaxies, but they're still in their infancy, so are still developing. But we see some traits that are common to galaxies even today. You see in the center of this main galaxy, there is a sort of red ball. This is what we call a spheroid, and it's made of stars. And around it you see this gas that swirls around and circles, and it will eventually form the spiral arms of a galaxy like the Milky Way. And in all this, you see also that black holes inhabit. These white dots that go around, these are black holes that are interacting with each other. They're trying to grow in mass. Unfortunately, since these black holes are very tiny, you cannot see their growth in mass, but they are growing in mass, trust me. And they're also merging with other black holes when they get close enough. Now, at this point, the galaxy looks like a reputable galaxy. You can see the whole disk in which we have stars, we have gas. At the center, you have a nice black hole, and then you have a few stray black holes here and there. Stray black holes in galaxies? Yeah, we really expect them. Not many. You see here 2 or 3 for a Milky Way. But that's a common prediction of all our models. What I said, this is a prediction. So we theorists say they should be there. Proving that they are there That's a very hard job because they're very faint, so it's very difficult to see them with our telescopes. But there are several groups in the world that are trying to see if this is true or not. If it's not, we have to go back to scratch and revise our models. And it's okay, I mean, it's life. We have to understand how physics works. So this is basically the picture that we want to have. Trying to start from the very beginning with first principles and evolve the universe to see how it looks like and find something that is not seen yet. And this means it's a prediction, and if it is verified, that it means that the rest of our theory is probably not too bad. If it is proven wrong, we go back and learn again. So the starting point is how we form black holes. So you saw in the movie that at some point these white dots were appearing in the galaxies. So there is some sort of magic wand. No black hole, black hole. What is doing this? How can you turn something that is not a black hole into a black hole? We know only one way that is easy. You take a star, at the end of the life, it becomes a black hole, provided this star is about 10 times the mass of the sun. But a black hole with a mass of 10,000 times the mass of the sun, how can it become 10 billion times the mass of the sun? It doesn't make the cut. So we have to be a bit more inventive. So we have to think of ways in which we can make a black hole that is more massive than 10 times the mass of the sun using what we have at our disposal. Point 1, physics. Point 2, gas. 3, stars. 4, dark matter. This is everything we have, nothing else. So a few years ago, in 1978, Martin Rees, who was one of the fathers of galaxy formation, black hole evolution, and so many other things that I cannot list them, in a seminal paper proposed different ways in which you can turn a gas cloud, sorry, this is very hard to see, but it was technology of 1978. You start with a gas cloud, and then you end up at the bottom with a massive black hole. As you see here, you have different ways of going through this process. It's all physics, there is no magic, but still you can turn a gas cloud into a black hole. I mean, the simple way of thinking how a gas cloud turns a black hole. Now, if you are very, very strong, you take a piece of gas, you compress it, compress it, compress it, compress it. When its size becomes less than the Schwarzschild radius, than the event horizon for that mass, you have a black hole. Now, this, I promise you, doesn't work. We tried. No way. We have to find ways that really use gravity, but in a very inventive way. Now, this is what Martin Rees proposed in 1978. Now we are about 40 years later, and these are still the same physical processes that we study. This is a small update from one of my papers in 2012. Actually, it was, I think, the paper that Peter mentioned, in which I put the same physics that Martin suggested, but in a cosmological context. So you see here, I don't start anymore from a gas cloud, but I start from a dark matter halo with gas in it. This is how we think the first galaxies formed. So if this first galaxies formed out of this, the first black holes should also form by the same stuff. So here I just used 4 methods, and there are, at this point, I mean, this is 2019, I stopped counting how many models have been proposed, but they all pretty much are variations of these 4. In all cases, you start from the same initial conditions, so a dark matter halo with some gas in it. This is what how all galaxies start with at the very beginning of the universe. And then you can follow different paths to form black holes. For instance, the one at the top is just the easy one. It's just normal star formation. You form stars in these galaxies explode, they leave behind black holes. But the most massive that you can make, even stretching all parameters, using some shortcuts, is about 200 times the mass of the sun. Still not that much. So then we became a bit more inventive. Okay, we have seen stars turning into black holes. Good. Now we try to find something more effective. We take the same amount of gas. How can we make a black hole out of that? Well, a good way is to form a star that is very, very massive. So normally when you start, if you think of a galaxy, I showed you movies, I showed you pictures of the Milky Way, you have many stars in a galaxy. But if you form only one star, that star will be very, very massive. Now, this can happen, but it can happen only for galaxies in the very early universe that are in very specific conditions, that are very nearby other galaxies who also have some specific conditions. So it's a very, very rare process. But in about one galaxy out of 1 million, all the gas can go in and form one star with a mass of about 1 million times the mass of the sun, up to 1 million times the mass of the sun. This is what we call direct collapse. And this is the second model. It's a kind of magic, but it's not. And in this case, as I said, it's very rare, but you can form a big black hole. So the two models at the top are the two extremes. Easy science, easy physics, so many of these, but small black holes at top. The second, very, very rare, but very, very massive. And the two in the middle are kind of in between as well, in the sense that they require conditions that are also a bit rare, because the third one requires you to form a nucleus. Remember when we zoomed in the center of the Milky Way, at some point the distribution of stars was very, very dense? We call that a nucleus. If we make that a bit more dense, stars don't have anywhere to go. The only thing they can do is collide with another star and form a more massive star by mergers. If you repeat this process, you can form a very massive star, up to about 1,000 times the mass of the sun. So with this process, you can form black holes with a mass of about 1,000 solar masses in about a galaxy every 1,000. And the last model is very similar, except that you merge black holes instead of stars. So what differentiates all these models that go from nothing to black hole are two things: the mass of the black hole that you find, 200 times the mass of the sun, 10 to the 6, about 1,000 and about 1,000, and how often this process can happen. The one at the top, easy. The second one, super rare. And the two at the bottom, kind of often. So when we put this together, if you remember this figure that I showed you at the beginning, where there was the orange bump and the blue bump, which is the observed black holes that we have today, now I put these models as well. So here we go. The one on top in the previous slide is shown here in green. So small black holes, but a lot of them. Then we go to the two intermediate cases, and then to the rare but big black holes case. Now, the numbers are not important here, but the cool thing is that if you think about it, all these models fall in the hole that we have in between the observations. So theorists, we predict, we say that there are black holes in there. There should be black holes in there. That's the way, these are the bricks that you use to form the more massive black holes. How can we find them? Well, that's my endeavor. That's been my endeavor as well for many years. That's endeavors of many observers. And now I will give you some hints of how we can do this with different techniques. Now, it's very, very hard to find a black hole at the time of formation. But we can find traces of the first black holes using other signatures, just not much later, much after they formed. And usually we can see this through two different types of instruments. One is telescopes, what we have used for many years and for studying black holes since 1963. So we can see photons, infrared, radio, optical, ultraviolet, X-ray frequencies, and even above. Or, as of recently, we can use gravitational waves. What we say is that with gravitational waves, we don't see them, we hear them. it's not something that we can see, but we can still measure them in a sort of frequency way. So as black holes grow in mass, we can trace their growth using those two different signatures. When two black holes merge, they will emit gravitational waves. Well, they have emitted in the past, and we will detect them in the future when we have the telescopes. But also, as I said, every time black holes eat a little bit of mass, which is not a black hole, everything other than another black hole, they will produce light. So whenever black holes grow in mass, they emit a signal, either in gravitational waves or in light. And that's how we can trace them. We can trace exactly their growth. Let's start with the first signature, gas secretion. So black holes that are growing, that are eating some gas, some stars that pass nearby, mostly gas, really. I mean, black holes can eat some stars, but it's a very rare event. Mostly you have gas it's around the galaxy. You have seen the simulation, right? The green gas was pretty much everywhere. So some of this gas can occasionally get close enough to the black hole that it is captured. Where close enough is about 1 light year in a galaxy that is 10,000 light years. So it's something that happens every now and then, but we should not count on it too often. As I said, our black hole has not been eating at all for the last 2 billion years. So gas is the main source of food for black holes, but not only. Gas is also the main source of food for stars. Well, in reality, gas is actually what forms stars. If you have gas that is dense and cold enough, you form stars. Now, in principle, you have this amount of gas in the galaxy. You can use it either to give it to the black hole grow, or you give it to the stars and say stars form. In fact, usually it's the stars that win. It is much easier to form stars than to feed black holes. So usually there is this fight between galaxies, between stars and black holes who can use this gas for growing. And since gas is used to form stars, as time elapses, the amount of gas that you have decreases and the amount of stars that you have increases. So when we think about galaxies in the past, the fraction of gas over stars was higher. This means that also the probability that some of this gas went to the black hole was higher than today. This is why I said there was a cosmic noon. About 5 billion years ago, most black holes were growing because there was so much gas around that even if stars were forming, and they were forming a lot of stars, there was still some gas left for the black holes. Nowadays, well, stars don't form that much because there is not much gas, but black holes are also not eating much. So it's really a matter of how galaxies evolve as a function of time, how you turn something into something else. You turn gas into stars, you don't have any gas left to form more stars or to grow the black hole. So this is part of our cosmic history. But what did all this evolution lead us to? This is a picture of what we know today of black holes in our local universe. Local universe means really a small bubble, a few billion light years from us. And here, this figure shows the mass of the galaxy at the bottom and the mass of the black hole vertically. Large galaxies on the right, small galaxies on the left, large black holes on top, small black holes at bottom. So here we see that big black holes live in big galaxies and small black holes live in small galaxies. So this means that over time, this pattern of turning gas into stars, of turning some of the gas into black holes, was clocked between how much mass goes into stars and how much mass goes into the black hole. We have some sort of scale. If you take the black hole mass and we multiply it by 1,000, we get the galaxy mass. On average, this is kind of true. So this means that there was something telling, okay, you eat 1, you eat 1,000. What was this? This has been the source of many, many studies in the last probably 20 years, but especially since 2005. And this has to do with regulation of gas consumption, what we call feedback, something that feeds back into something else. The way we can think about it is that you produce something out of what you have, in this case energy, and this energy goes back into changing your initial conditions. So here what you see is what we call the pillars of creation, or the Eagle Nebula. This is a very dense gas region where we know stars are forming right now, or at the time when the light that was emitted happened. We know that stars are forming in the center of these clouds because you see from the very top some rays of light coming out. These are stars that are very young, that are still enshrouded in this dense gas, but some of their rays are poking holes in this cocoon of gas that is surrounding them. So here we have some gas that is dense and cold, and we know that it's dense and cold because it's very dark. From this dense gas, you form stars. Stars start emitting light. Now, light is a form of energy. It will interact with the gas. It will heat the gas. Whenever you give energy to something, it gets hot. It also, whenever gas is heated, it will expand. So you start from gas that is dense and cold, and you end up with gas that is hot and rarefied. Gas that is hot and rarefied, not good for forming stars. So the simple fact that you have formed a star eventually will prevent more stars from forming. This is what we call feedback. The energy given back by the stars will prevent further star formation. And at the same time, it will also prevent this gas from reaching a black hole. The same is true for the energy that is produced by the black holes themselves. I told you again, this 10% of mass that goes into black holes is actually turned into energy. The most efficient engines in the universe. This again is true. So not only stars produce ultraviolet light, not only stars produce explosions and winds, black holes do the same. This is a case, this is a very famous case. It's a black, all this, you see this purple, red light, jet. This is the energy that was produced by the black hole at the very center of that galaxy. It extends for about 1 million light years. This is a huge amount of energy that is injected into space. This energy is also, well, energy. It's photons, it's light, it's energy, is thermic, and thermal energy is heat. And it also has the same effect on gas. Gas that was dense and cold turns hot and rarefied. So this gas now cannot form stars. This gas cannot feed the black hole. So it's the effect of their own feeding that eventually stops black holes from growing more, stops galaxies from growing more. So it's what we call very often either the feedback cycle or self-regulation. So we really think that this is what sets the scale. That galaxies and black holes know about each other because they regulate how much they eat each. And it's very subtle because, again, if you think of black holes in terms of physical size, they're tiny in the middle of galaxies. They should not know. Causally, they should not know how galaxies evolve in mass, but they do through this energy injection that happens in both cases. So, using our telescopes, we can follow how black holes grow from their formation to today through these phases of growth. But we cannot follow them when black holes are not eating some gas. We have then the other option, which is using gravitational waves, which is not checking what happens as the black holes grow, but when they merge with another black hole. So, since 2015, this has been very important for us because it had a completely new window to look at the universe. This is a simulation showing the merging of two black holes. You see here these ripples of space-time, these gravitational waves. They propagate at the speed of light, and they really change the shape of space-time. When you have a gravitational wave passing through space, it will just stretch and release space-time. So it really changes the length of space between two things. And this is the way we detect them. So we have seen with LIGO, there has been a lot of excitement, so I think that all of you have heard about it, has detected merging black holes emitting gravitational waves in the last 4 years. Now there are tens of these mergers. But these are not my black holes. These are tiny black holes. To see my black holes, we need other telescopes. We need other gravitational wave detectors. So here in this slide I put together the collection of gravitational wave detectors that we have now, LIGO here, bottom right, and the two that are planned in, well, one is taking already information, and I call it information because it's a special way, and one is planned for 2034 that can detect gravitational waves from my black holes, from massive black holes. So you see here that these different instruments are characterized by a different frequency. It's really like, frequency for radios. You need to have the right radio to detect the right frequency. And different black holes emit gravitational waves with different frequencies when they merge. In fact, the more massive are the black holes, the lower the frequency at which they emit. If you're a fan of equations, top right. If you're not, big black holes, low frequency, and vice versa. So you need to build the right detector to detect the right frequency. LIGO, the one that we have on Earth, detects frequencies that are characteristic of stellar mass black holes. These are about 1,000 Hertz black holes with a mass of about 10 solar masses. As I said, more massive black holes, lower frequencies. So the two instruments that I'm going to describe now go to lower frequencies. Now, another interesting thing about frequency is that it doesn't scale only with black hole mass, but in general, it scales with. So if you want to detect a given frequency, you need an instrument that becomes larger and larger as the frequency becomes lower and lower. It's an effect of arm length. So if you want to detect a lower frequency, so more massive black holes, you have to build an instrument that is bigger, much bigger. LISA, this is my favorite instrument, sorry, I'm partial here, but I've been working on this for too much time. So this is an ESA mission. It's planned for 2034. It's like LIGO, but in space. So you have two lasers that are L-shaped. So if you think of a gravitational wave passing through space, one of the arms will be stretched in one direction, but the other will be stretched in a different way. So the time that it takes for the lasers to start, go out, and come back will be different if a gravitational wave passes through this way or this way. So this is how we think we want to detect this. So it's the same principle as LIGO, so we know that it works, but now we need to have a size of our arm of about 2.5 million kilometers. We do not have 2.5 million kilometers on Earth. So we go to space. That's why this is a mission that is from ESA, European Space Agency. You have to build a satellite, launch it in space, and then you can have these lasers put at a distance of about 2.5 million kilometers and see what happens to the timing of these lasers. The other instrument that we have is called Pulsar timing arrays. So while LISA can detect black holes with masses 10,000 to 10 million solar masses, Pulsar timing arrays can detect gravitational waves from black holes with masses of billion times the mass of the sun. As I said, big black holes, low frequency. Low frequency, you need a big arm. To detect these black holes, you use the whole galaxy. Our detector is the full Milky Way. This is a very clever experiment that uses pulsars. These are neutron stars that rotate and work like lighthouses. When the light points towards you, you see it. Otherwise, you don't. So you can really time how often you see the ray of light coming in your direction. There are some pulsars that are very, very regular. Now imagine a gravitational wave passing through a galaxy. It changes the length of space in the galaxy. So if a pulsar is in the path of the gravitational wave, will not be seen by us at the same time. So if we see glitches, so if at some point, all the pulsars in the Milky Way point towards us at the wrong time, something has perturbed the space-time of the whole galaxy. The only thing that can do that, a gravitational wave. So that's how people have been taking data for many, many years now, trying to find this signal. We haven't got one yet, but we expect to see something in the next 10 years. So between, late 2020, early 2030, this will be the golden age for gravitational waves from massive black holes. And what is the cool thing, or at least for someone like me, is that they can see something that we have never seen before. Now, this figure here, which is very busy, shows what LISA and these pulsar timing arrays can see as a function of the properties of black holes. So here on the right, you have cosmic time. This is about 200 million years after the Big Bang, and this is today at the bottom right. And here you see the lives of some black holes. They form at the very beginning of the universe with very small masses, and then they grow in mass as a function of time through accretion of gas, this process that makes quasars, makes black hole grow. And this you can see when you have a smooth change in the mass of black holes, or by mergers with other black holes. And these are the dots that you see. Now, the whitish, light blue whitish part is what LISA can see. Then what we can see with our telescopes at all wavelengths is shown here on the bottom right. This that says future electromagnetic probes. And then pulsar timing arrays can see really the small orange area at the bottom. But so with an instrument like LISA, we can see a bit of the universe that we cannot see with photons, we cannot see with our telescopes. In particular, we can really see the time when the first black holes formed. All these models that we could create because we have no data to constrain them, so we could be creative. This is how we can see whether we're right or wrong. Whether all these models that we started studying in 1978 are a good, correct representation of reality. And so this is really, to me, something very exciting. I will finally see whether my work is correct or wrong. And it's fine. I mean, I can be wrong, but the important thing is that it's physics. So here I will just conclude with the journey of two black holes to merge together. Gravitational waves detect merging black holes. Merging black holes in the supermass, in the massive variety, it's a very complex problem. It's also something we started studying in 1980, and we still haven't solved yet. The reason is that it includes lots of physical processes, lots of scales. You need a full cosmological context to see how often galaxies merge, because each galaxy hosts a black hole. So to see a black hole merger, you need a galaxy merger first. The physics of galaxy merger is very, very massive. Messy, not massive. It's something that you cannot study with just pencil and paper, in the sense that it's very often chaotic. So you need cosmological simulations to study all this. And then we get to the physics of black holes forming binaries in galaxy centers. Again, if you think of the movie going towards the center of the Milky Way, you remember that bit in which there was this dense blob of stars, very, very dense. Now, the interactions of black holes with these type of blobs, which are called nuclear star clusters, is one of the most fascinating types of physics that we have. It's really strong dynamics, and you can be very, very creative with all the processes that happen there. Black holes flying in and out, gas stars that fly even faster. And so this is why this is very complex problem. It's even more than black hole formation, really, and it's more interesting. And then eventually get to black hole mergers. So this is what I think will be the next frontier of studies of black holes in a cosmological context for the next 10-ish years until we get to observations of gravitational waves, and then we can start seeing whether these models are right or wrong, and check whether we find these merging black holes in merging galaxies, whether we have black holes that fly in the center of galaxies or near the outskirts where we are. So these are all predictions that we have, and we're looking forward to seeing whether they're right or wrong. And so I hope that I showed to you that black holes are still very fascinating, although we have detected at this point hundreds of thousands of them. We have measured the masses of many, but we still have mysteries on their formation, on the dynamical evolution, and I think that this is where we will concentrate our efforts in the next 10 years, so stay tuned. Thank you very much.
I seldom was at a lecture where the people were so quiet. So either you were sleeping or you were extremely fascinated. And I think you were all extremely fascinated. Thank you very much. So there is time for questions.
So if there are any questions, you can just stick your hand up and I'll come forward.
Thank you. How do they affect us?
Us? Not much, especially today, since they are very quiescent. There has been some studies that have looked at whether the production of gamma rays from some of the massive black holes, from the black hole in the center of the Milky Way. There were some studies looking at the production of gamma rays and how that would have impacted a civilization active at the time. And yeah, gamma rays produce mutations, so it's not good for us. But since our black hole has been quiescent for about 2 billion years, I think that at this point we're rather safe.
So we live in a sort of a habitable zone in the Milky Way, yeah?
Yes.
Rather quiet where we are, so if we go too
Very close.
close in, then it becomes really dangerous.
Is this process of black holes having an influence on the process of expanding or enlarging the universe, or is this process of forming black holes also an element and maybe a process of contracting the universe eventually?
The amount of mass in the universe that is made of black holes is super tiny. It's about a millionth of the total mass that we have in the universe. So they cannot have influenced the gravitational evolution of the universe in this function of contraction. But vice versa, the conditions for forming black holes occurred only at certain times in the universe. Now, in fact, here, I focused on astrophysics. So all these processes of black hole formation require very young galaxies. And this happened when the universe was much denser. So in this case, it's the density of the universe that makes it easier to form dense galaxies. And if you have dense galaxies, it's easier to form black holes. So this is true. There are also some models of black hole formation that do not require galaxies or stars or gas at all. These are based on singularities that happen at the time of inflation. So again, also in that case, it's more the universe that influences how black holes form. Now, in some of these particular models, again, this is not astronomy, so this is not my field, all the dark matter in the universe is made of tiny black holes. So in that case, yes, black holes become influent, but not the massive black hole variety that we see here. It's very, very tiny black holes.
More questions?
Professor, could you please explain how in the early universe supermassive stars have been in existence? Because in the local present-day universe, they cannot exist above some 300 solar masses because they blow themselves up via radiation pressure.
Oh, that's correct. So when we say that, so first again, the model that produces these very supermassive stars requires very special conditions. In particular, you can form a quasi-stable supermassive star if the situation is not quiescent, in the sense that the star must be bombarded by mass falling in. So the picture that we have in mind is that you have a star forming in the center of a galaxy. The galaxy itself is unstable, and so it rains down, it throws in mass to the star. So the star doesn't have time at any point to relax into a normal star. It still produces nuclear reactions. It grows. It actually, this is a bit more technical, but it emits most of its radiation in infrared rather than ultraviolet, which is not such a big source of energy. So that's why material from the galaxy can continue accumulate around the star. So you have this star in the middle, and you keep on accumulating more and more gas around it that gives more gravity. So that's how you keep this system from going immediately into an explosion, basically. So, as I said, this may happen. Theoretically, we can simulate this. How often this actually happens, unclear to me. But yeah, it's definitely not a normal star.
How massive can they be?
Depending on the models, up to 1 million solar masses. I mean, 1 million times the mass of the sun. And it stays a star for just, I mean, the moment you stop accumulating mass, it goes through a gravitational instability, a relativistic instability, and it collapses immediately into a black hole. So they're very short-lived as well.
Could our Milky Way inhabit a second multi-million black hole?
Sorry, I couldn't hear you.
Could our Milky Way inhabit a second?
Oh, yeah.
Milky Way?
Oh, yeah, there could be. Well,
flying around, being unexpected.
well, so let me go back here. So this is a theoretical picture. So this is simulation, and this is a Milky Way-like galaxy. And so we predict that there are a few black holes out there. Now, we can rule out the existence of the second black hole very, very close to the black hole that we have now, just because we can see the stars moving with this very high accuracy. As I said, theoretical models predict them. There have been some claims recently of an object not far from the center of the Milky Way, a few hundred light years, I would say, and which has peculiar motion. And there's been speculations that it's a secondary small black hole, about 1,000 solar masses or so. It could also be a very dense region of star formation. So it may be. It's not ruled out. Our predictions, I mean, not when I say our, it's not just my group, it's pretty much everyone who does this type of models, predict that there are, in the Milky Way you have 4 or 5 of these objects floating, mostly outside.
So another one here in the back.
Thank you. What is the evidence that the massive black hole of the galactic center has been quiescent for 2 billion years? I mean, I understand that there's a very clumpy, cloudy interstellar medium in the central region of the galaxy, and these clouds have a large random motion. So might you not expect a cloud to encounter the black hole now and then and flare up?
Okay, so there are two things here. So the dating of its past activity, it's from fossil evidence. We don't see any remnant of this past activity that we can trace. We don't see outflows that were created by the black hole. We know that the galaxy has been very quiescent also in terms of star formation. But then in terms of the gas content, this is a big mystery. Now, the center of the Milky Way is extremely rich of gas. And it's also called dense gas. It's the perfect gas to feed black holes. So why isn't gas actually going towards a black hole? This has been, very puzzling for many years. So this is called the cold molecular zone. So you really have a lot of gas. It's perfect gas. It just doesn't go there. The reason most probably is that this gas has too much motion, too much velocity, too much kinetic energy, rotational energy. So it actually keeps on orbiting without actually going in. So to feed a black hole, you need also very specific orbits. In terms of stellar dynamics, more than gas dynamics, we call this the loss cone, the cone in which you can lose stuff, lose meaning going into the black hole. And it requires specific conditions of energy and velocity. So not all orbits, so basically think about it, you have a black hole, anything that just orbits this way will never make it. The gas or the star has to go straight toward the black hole. In terms of fraction of orbits of star and gas that can do that, this is a small fraction. That's why we call it a cone out of the 4 pi distribution of orbits that we can have.
Are black holes that have an accretion disk able to sustain a solar system?
Able to, sorry?
Sustain a solar system, much like a sun, for example.
The presence of planets, is this what we're asking? Okay. Because, in terms of habitability, I think that Peter was saying that they will not be the most hospitable place. So yes, there is the possibility that inside an accretion disk you form stars. Actually, it's a very high probability. In fact, there were also models about the former accretion disk of the Milky Way creating these stars, the S2 star that I showed you. So we expect that stars can form inside accretion disks. Whether these stars then can form planetary systems, that's a bit more complex. What we expect is that these stars carve a little hole around them in the disk. So in principle, they are kind of in their own bubble, so they can evolve in a normal way. But also these stars are expected to have kind of weird masses. They should be more massive than normal stars, so more massive than the sun, just because of the type of environment they're in. So this is the current theoretical expectation. Of course, there's been no detection of that.
I have a question regarding the gas. Since you said the gas also like the dense and the cold gas form the stars, and also the gas is like the food also feeds the black hole. So I wonder what produced the gas in the very beginning in the universe, and where this gas originated from. Thank you.
Okay, so all matter was originated in the Big Bang, or at least this is what we think. And the fact that as the universe evolves, the way you form, you don't start with gas. We start first with a plasma. This plasma then eventually, as the gas cools down, as the universe cools down, you can start forming first nuclei. This is called primordial nucleosynthesis. Then if as the temperature decreases more and more, these nuclei will form atoms. Now, once you form atoms, this is what we call gas, meaning that at that point we have formed hydrogen. Hydrogen is a gas at high temperatures. And so this is what will form all the structures that we see later on. So this, at the same time, hydrogen, gas, all these represent only about 15% of the mass of the universe and 5% of the energy of the universe. Most of the mass is still in dark matter, and most of the energy is what we call dark energy. But gas is just a product of the cooling down of the universe over its whole evolution. And this has happened very quickly after the Big Bang.
So this was a wonderful talk. I particularly noticed, though, that you often skipped over that gap between the solar mass, the stellar mass black holes and the massive black holes. And even in the plot of the instruments, there's a gap between LIGO, Virgo, and LISA. So how are we going to find the 1,000, 2,000, 5,000 solar mass black holes?
Well, LISA can see 10 to the 4 solar masses black holes, but yes, the third generation of gravitational waves instrument detectors is aimed exactly at these objects. It's called 3G. I mean, at the moment there are concepts because it takes time to develop them, but these are detectors that are in between the size of LIGO and the size of the Earth, basically. And in principle, they are aimed at detecting mergers between black holes between 100 and 1,000 solar masses. So if they are there, we will see them, except that perhaps it will happen when I'm close to retirement.
Professor, is it conceivable that supermassive black holes have become so massive by devouring large quantities of dark matter?
It's conceivable, but it's not probable. In the sense that, as I said, for black holes to eat something, it has to get very, very close to the black hole, which means that usually it has to dominate the amount of mass that you have around. Now, if you look at galaxies, outside, the outer regions are mostly dominated by dark matter. But as you get closer and closer in, the fraction of mass that is dark matter compared to gas and stars decreases. So at the very center, normally we are dominated by gas and stars. So it's more probable that black holes accrete gas. This is because dark matter is what we say, well, it's dark. So it doesn't emit light, and light is a way for normal mass to get colder, and if you get colder, you get denser. So dark matter cannot get very, very dense because it cannot get very, very cold, because it cannot emit any light. So this is the simple explanation. However, we don't really know. I mean, what we see is a black hole lights up. What it has actually eaten, it doesn't say so.
I've seen one more. And
thank you. I wonder, is the quality of the galaxy, of one galaxy, stay the same?
Sorry,
the quality of the galaxy stay the same during the process, like the massive black hole eating and exploring, but is the quality stay the same?
Properties of the galaxy, you mean?
Yeah. The quantity, quantity. Yeah, quantity.
I'm not sure. The total mass?
Am I making my question clear?
No, I think that the quantity is not something. I mean, you mean the total mass of the galaxy?
Yes.
Okay, so are you asking whether when the black holes become active and produce energy, some of the mass in the galaxy is ejected?
Yes, because if you eating something and something observed by the black hole, but the material is still there.
So, no, the material actually goes into the black hole.
But yeah,
if you take an atom. Let's take an atom, which is just simple. It crosses into the black hole, it goes into the black hole, it becomes black hole. Then 10% of that mass becomes energy. This energy goes out. So are you asking if this energy that goes out takes away something from the galaxy?
Yeah, I really wonder, like, if you weight something, the quantity,
so if you weight, okay, so if mass goes into the black hole, you weight it and it's heavier. Okay. Now, the amount of mass that goes into a black hole in terms of galaxy mass is small. So the black hole mass is about 1,000 times less than the galaxy. So the mass that disappears because it goes into the black hole, it's nothing for the galaxy. I mean, it's just a tiny little amount. However, it may happen that some of these winds, that this energy that is created by the black hole, can capture some mass as it propagates out. And if these winds, we call them really winds. It's like something very energetic that moves very fast. So sometimes it can take away some of the mass of the galaxy. But it's a secondary effect. The amount of mass that goes into the black hole is a tiny amount. It's 1,000th of the mass of the galaxy.
Just a quick question. So in this picture, you have the black holes kind of hanging out in the outskirts. But I think what you were saying earlier is we only will see them if they eat something or if they collide with each other. So do we have to wait for two galaxies to collide with each other to see their outer orphan black holes colliding? Because we can't see them in our Milky Way.
That's the point. I
Okay.
mean, that's why I said this is a prediction.
Okay.
But it's very, very, very hard to test it because these black holes will be very faint because they are in the outskirts of the galaxy. They have a very small probability of capturing something else. So
even if you build this intermediate one that should detect them, you still might not.
We may have to wait some time before we can see them, yes.
And orchestrate a collision, yeah.
So I propose that we continue the discussion downstairs. We will be providing drinks for everyone. If time, please come down and have a drink with us and with Professor Volonteri. I think there's also something to eat, so you will also be fed. And we do not expect feedback.